Okay, so now that we have covered the azimuth and the altitude, let's start to take a more distinct look at the path of the sun in New York State and some other latitudes, along with the duration of sunlight that we get. So these things are really intertwined, right? So if the sun's out for a long time, that means its path is going to be very long. If it's out for a short time, its path is going to be very short. So for this, I'd like for you guys to turn in your note packet to page 22. Page 22 in your note packet. I know it's quite a bit ahead, so I'll give you a second to get there. Pause the video when you're at page 22. We'll pick it up from there. Great. So on this page here, I want you to pay careful attention in your notes of what we're giving you here. So we have the 3 paths of the sun, and we also have the altitude of the sun. So before you start writing and drawing, this is a time where I would highly encourage you to grab 3 colored pencils, a blue one, a green one, and a red one, and then go ahead and draw these lines. Now, some of you are going to sit there and say, Mr. Gulitzer, that requires me moving, and that requirement just crosses a line for me fundamentally. I don't move at all. So if that's you, I apologize. I didn't mean to offend you. But if you are able to get up and grab some colored pencils, that would be excellent, because keeping track of these use of color, I find, is one of the best ways to learn them. So if that's you, pause the video, go grab the colored pencils. They should be right up in the front of the room by the index cards that are right on the desk in front of my smartboard. Grab yourself some and come on back. If you have the pencils now, or if you're not going to get them, this is the apparent path of the sun changes with seasons and with the latitude. So New York State, I put 43 degrees. You know that we are 42 degrees at Mayville, so that's fine if you want to put Mayville. So I just label what we have here. New York State, I also put my directions on here. I put north, south, east, and west with my red pencil, because to me summer means hot. I drew a line. Notice that it's rising north of east. The sun here is stretching up to an altitude of about 70 degrees, and then it's coming back down, setting north of west, big long arc, big long day. Summer solstice, of course, is the day we're looking at here with the red line. The green line represents both equinoxes, both the spring equinox and the fall equinox. On these days, the sun rises due east, and it sets due west, and it reaches an altitude of 47 degrees. The winter solstice, I put for the blue line here, representing cold temperatures. Get it? No? It's okay. Blue, winter solstice, it rises south of east and it sets south of west. It climbs to a height of 23.5 degrees in the sky. You guys are going to need those numbers. You're going to want those numbers when we do the lab on Thursday, I promise. So please make sure you're taking time to write these down, so that on Thursday you're not like, well, where do I find these? Can I Google them? And they're right here for you. The equator, the path of the suns are vertical. So here we have the sun getting to these different altitudes. Well, there's really 2 different ones, but we have the sun getting these different altitudes. We notice that their paths are completely straight up and down. They're completely vertical. This stands in contrast to the path of the poles when they're completely horizontal. So the equator, the sun hits the zenith, which is the point directly on top, on September 21st, and then again on March 21st. So the equinoxes, the sun's vertical ray, aka the sun is at the zenith at the equator on those days. And those are also the days that everybody's getting 12 hours of sunlight. So even this big stretch across the sky here is only 12 hours long. Because if you think about it, it takes longer to go like this than it does just to go up and down, right across the sky like that. So the sun will migrate from March until June to another 23.5 degrees, which is the tilt of our Earth. So the sun moves about the sun moves 23.5 degrees per season. This will also help you on some of your labs coming up. If you're like, what are you talking about? I still don't understand. 90 minus 23.5 is 66.5 degrees. So that's where this number is coming from. So it's going to migrate over to 66.5 degrees, still the whole time doing these vertical paths, all the way through April, May, and then June. Then it's going to do these vertical paths back to here for September, then vertical paths back to here through the fall, until it gets here at the winter solstice, still 66.5 degrees. Still very, very warm. Okay, so that's why the equator doesn't have any seasons. All right, so guys, this really gets into the duration of sunlight. And I actually really like this page. One of the reasons I like to use the notes is a couple, but one of them is this page and the visuals that come with this. So I really like how the author here shows where the vertical ray is and then gives the duration of sunlight at these different latitudes. So the latitudes we're talking about here is got the Arctic Circle, the Tropic of Cancer, the equator, Tropic of Capricorn, the Antarctic Circle. So you can see here, March 21st, our spring equinox, the sun's vertical ray is hitting at the equator. And the duration of sunlight at all of these locations is 12 hours. So you should write this right in your notes, 12, 12, 12, 12, 12. This is also true of the fall equinox, September 21st. So you can see the sun's vertical ray is hitting the equator. We have 12, 12, 12, 12, 12, 12. Now on June 21st, the summer solstice, the sun's vertical ray is hitting the Tropic of Cancer. So this is going to change some things. So we have 24 hours at above the Arctic Circle here. We have 14 hours at the Tropic of Cancer, 12. The equator always has 12, no matter what time of the year. And 10 at the Tropic of Capricorn, and 0 degrees once you get above or below the Antarctic Circle. And then the winter solstice is a flip of that. So December 21st, they're getting 14 hours of daylight at the Tropic of Capricorn, 12 at the equator, 10 at the Tropic of Cancer, and then 0 degrees above the North Pole, and 24 hours once you get below the Antarctic Circle. And this chart, I love it, this table. So we have March 21st, June 21st, September 21st, and December 21st, and they're telling you the duration of daylight at all these different latitudes. Notice for the equinoxes, it doesn't matter where you are on Earth, we're getting 12 hours no matter what. Once we get into the solstices, this changes. Okay, so the equator always gets 12, so that's another 12 right here. So we got 12s across the board here, 12s across the board here, and 12 for the equator. And then we start getting into the more wilder springs, wilder shifts, I should say, of the duration of daylight. So up at the poles, 24 hours, 90, 80, 70, because remember the latitude of the Arctic Circle is 66.5 degrees, so we're getting 24 hours of daylight above that during June 21st. Then it goes 18, 16, 15. Notice it's getting closer and closer to 12 as you get towards the equator. And then as you get further away from that and towards the South Pole, you're getting less and less hours of daylight. On December 21st, it's just the flip. 0 degrees above the Arctic Circle, very few hours at the northern latitudes. When you get to our latitude or close to it, it's about 9 hours. And then so on until you get to the extremes of 24 hours below the Antarctic Circle. So take a couple moments and write down these durations. I promise they will come in handy, again, as we work through the labs and also as you prepare for upcoming quizzes. Okay, the next page, they're saying the angle of insolation and the uneven heating of the Earth's surface. So if we have high angle insolation, now remember, insolation means incoming solar radiation, aka sunlight. So they're saying the angle of sunlight heats the Earth's surface differently. So a high angle of insolation, high angle of sunlight, we have high intensity. And a low angle, we have low intensity because you're spreading the beam out over a greater area. So remember in class I was talking about telling a ghost story with the flashlight up to your face versus shining it right into your eyes. Well, once you flip the flashlight to your eyes, the intensity becomes much more concentrated, becomes harder to see versus the glancing the glancing rays off of your face. So the intensity of insolation is greatest when the sunlight or insolation is perpendicular. Perpendicular means to the Earth's surface. In other words, striking at 90 degrees, because the sunlight is concentrated in the smallest possible area. And as the angle of insolation increases, the intensity of insolation also increases. So we want you to then draw a line showing this relationship, angle of insolation versus intensity of insolation. Go ahead and do that. And you can kind of see it from my messed up triangle here. We're going to have a direct relationship here, guys. If you increase the angle of insolation, you increase the intensity of insolation. Moving ahead, if we were to, one second. The other factors affecting the angle intensity of insolation are the shape of the Earth. So low angle of insolation up towards the high latitudes as you get closer to the poles, so you have low intensity of insolation. At low latitudes, like the equator being the lowest at 0, you get a high angle of insolation, a high intensity of insolation. Just here for a second. So as latitude decreases, the angle of insolation increases and the intensity of insolation increases. So down below, we give you some graphs, angle of insolation and the intensity of insolation versus latitude. Go ahead and fill in what you think you know of those. We'll reveal them in just a moment. Okay, so for both of these, you're going to have an indirect relationship. So the angle of insolation is greatest and the intensity of insolation is greatest at the lower latitudes. So you have an indirect relationship. Okay, next we're going to have you guys actually work through, let me see here. Yeah. Well, no, we better get this one. Okay, so the factors affecting the angle and intensity of insolation are also the seasons of the year. As the Earth travels along its orbital path around the Sun, the angle of insolation at a given latitude changes with the seasons. This depends on how far a given latitude is from the direct rays of the Sun. That's the vertical ray. The vertical ray, or the direct ray, migrates between the Tropic of Cancer and the Tropic of Capricorn. So, location of direct ray, Tropic of Capricorn. The latitude of that, 23.5 degrees south, and the date is December 21st. I want you guys to fill in number 2 and number 3. I think you can do that. And once you're done with that, I would take a look at the maximum angle of insolation at 12 noon. So this 12 noon is when we get our strongest sun. So on December 21st, low angle, low intensity. March or September 21st, medium angle, medium intensity, and June 21st, high angle and high intensity. Okay, we'll have you guys get those down. See if you need any more of this. A little bit. I'm going to come back to page 27 a little bit in the next video. Then we're actually going to take this and start doing some practice with it, okay?